Welcome back to this Forge College Explainer. In our last lesson, we tackled deterministic state transitions. Basically, the high-level rules of the execution game. But, rules alone don't store data. So today, we're crossing that bridge from abstract code to the cold, hard, physical reality of where your state actually lives.
It's a pretty fundamental question. We know execution semantics rely on reading and writing state, but where is it actually living? To truly optimize your smart contracts and, let's be real, to stop burning cash on unnecessary compute costs, you have to understand how your data is physically organized underneath it all. I mean, you can't organize a massive library if you don't even know what the bookshelves look like, right?
So here is our engineering blueprint for today. We're going to cover where state actually lives, addressing and update primitives, a comparison of drawers versus filing cabinets, real-world update scenarios, costs and write amplification, and finally, how to optimize your state layout.
All right, starting right off with Section 1, where state actually lives, the physical substrate.
The absolute first concept you need to wrap your head around here is the addressable unit. By definition, this is the minimal unit of persistent storage that the runtime environment can distinctly read or write. It's literally the hinge that connects your high-level code to the low-level storage. It dictates exactly what counts as one single atomic piece of data.
Moving right along into Section 2, addressing and update primitives are rules of engagement.
What's really fascinating here is that the runtime completely dictates the operations available to you, entirely based on the environment's architecture. You basically have two distinct patterns. In EVN-like environments, you're working with a sparse, slot-addressed key-value space. You read or write targeted individual slots calculated by a hash. But in SVM-like environments, it's totally different. You're dealing with account-centric, contiguous blobs. You have to load, modify, and store the entire account data as one big chunk.
Let's make this a bit more concrete in Section 3, drawers versus filing cabinets, our metaphorical blueprint.
To keep us from getting totally lost in abstract code, picture this. On one side, you have the EVM slot-addressed model. Think of this as a massive wall with thousands of tiny, independently labeled drawers. On the other side, you have the SVM account blob model. Picture a huge heavy metal filing cabinet that holds a single department's massive folder. This physical metaphor perfectly illustrates three absolutely crucial software engineering mechanics. First, atomicity and rollback. Fixing a typo in one tiny drawer is a breeze, but untangling a messy 100-page department folder, not so much. Second, read and write locality. How much effort does it take to physically pull your data? And third, parallel execution and contention. Two people can easily open different tiny drawers at the exact same time, but only one person can physically hold that giant department folder.
Let's take this into Section 4, real-world update scenarios, and apply this blueprint.
Let's look at Scenario A, our drawer model. Imagine you need to update 100 independent user counters. You're just quickly opening up 100 separate, independent drawers, reading the independent slots, writing the independent diffs. 100 different workers could technically do this at the exact same time without throwing elbows. It is incredibly efficient for parallel processing with zero locking conflicts.
But now look at Scenario B, the cabinet model. Let's say you just want to update a single user's avatar. Well, you have to haul up the entire department cabinet, load that whole profile into memory, tweak the name and avatar offsets, and then heave the whole heavy thing back. And the real kicker? While you're holding that folder, you completely lock out anyone else who's trying to access that same cabinet.
And here is exactly how those scenarios hit your bottom line. With many small keys, the drawers, your primary cost driver is simply the number of slots touched. Parallelism is super high, and the write amplification risk is very low per key. But with an account blob, your primary cost is the sheer size of the account being read. Parallelism becomes a major bottleneck, and the risk of inflating your costs for tiny little changes is remarkably high.
Which leads us perfectly into Section 5, costs and write amplification. Because eventually the bill comes due.
This brings us to a slightly terrifying bureaucratic nightmare known as write amplification. By definition, this happens when a tiny logical data change forces a disproportionately massive physical write operation to the actual storage disk.
Think back to our metaphor for a second. Imagine hauling out a 100-pound cabinet just to fix a single typo on a tiny sticky note inside. It's ridiculous, but that is exactly the equivalent of a 10-byte code change triggering a massive 1 kilobyte blob write to the disk. You're paying enormous physical overhead for a minuscule logical change, and that translates directly into painful transaction fees.
When you compare a tiny logical change across the two models, the difference is staggering. In a slot model, the disk I/O overhead stays small. It's just sliding open a drawer. But for an account blob, the physical I/O costs absolutely explodes. A tiny update in an account blob dramatically amplifies your physical operations compared to that sparse slot model.
So how do we fix this? Let's jump to Section 6, Optimizing Your State Layout, Engineering for Efficiency. You should keep these 3 highly practical principles tattooed on your brain when mapping out your storage layout. First, always identify your minimal addressable unit. Second, quantify your cost drivers. Ask yourself, are you paying for the blob size or are you paying for the key count? And third, ruthlessly expose and manage contention on your hot objects.
The core takeaway here is simple. You have to match your layout to your access pattern. Do you have high concurrency needs? Split those hot, independent fields into fine-grained slots. Use the drawers. But if you have group data that's frequently accessed together, consolidate them into an account blob to avoid repeated reads. Pack the cabinet.
All right, let's wrap this up with our conclusion and final takeaways.
Remember, your physical storage unit literally shapes your system's entire behavior. Slots versus blobs changes everything. Your costs rely entirely on the units touched, their size, and the runtime's bookkeeping. And ultimately, your layout choices directly dictate your total throughput, latency, and how safely rollbacks are handled under heavy network load.
I want to leave you with this final provocative question as you go back and review your own code. Does your current state layout act like a highly targeted drawer? Or are you needlessly hauling a heavy cabinet around for every tiny edit? Take some time to think critically about your architecture. Thanks so much for joining me on this Forge College Explainer. Be sure to visit forge.college to explore more resources and really master your Web3 engineering transition. I'll catch you next time.